Absolutely.
It's the Swedish government that's interested in having you come speak.
Got it. All right. And should I be muted when you let people in, or what's your preference for? I guess I see people rolling into the waiting room.
Perfect. We are being live streamed, so just keep this in mind.
Okay.
Yes, and then Lindsay, you can start letting in the people. There we go. Good morning, good afternoon, good evening, everyone. Welcome back. Everyone is entering the session. We see tens of people popping up in the waiting room still, and Lindsay is letting everyone in. Thank you so much again, Lindsay, for being there every day to organize all the tech for us.
Oh, and we have some more shout outs too, right?
We have many
Shout
shout
out
outs, and I received a whole list. We have amazing participants who are helping out now for the video editing. And brace yourselves, always, Juliana, Abba, Luis, Yining, Samira, and more. We are so grateful for your help in the video editing with Lindsay and Raj to make very beautiful videos available for all participants and beyond.
Awesome.
And then we will get started. Today we have a special session, not only about quantum computers themselves, but quantum beyond, the quantum internet and quantum biology, with two fantastic speakers, Prineha Narang and Clarice Aiello. Professor Prineha Narang is a faculty member at Harvard University. She is in computational condensed matter physics, where she designs novel materials atom by atom. Previously, she held positions at Harvard and MIT, and she completed her PhD at Caltech. She also won numerous prizes: the Mildred Dresselhaus Prize, Friedrich Wilhelm Bessel Research Award, Max Planck Sabbatical Award, UPEP Young Scientist Prize in Computational Physics, a National Science Foundation Career Award, Moore Inventor Fellow, Top Innovator by MIT Tech Review, and even more. In addition to that, she's an entrepreneur. She co-founded Aliro Quantum and is the CTO there, building the quantum internet of the future. Soon, she will move from Harvard to UCLA, and a UCLA student was actually the first to send a message on the normal internet. And now a question to all of you: how long was that ago? When was the first message sent on the normal internet? Still a tiny internet at that point. I will look at your answers on Discord. Was it 20 years? Was it 40 years? '70s, '60s. Lewis is right. It is approximately 50 years ago. The tiny ARPANET starting, leading to the internet that we have now. And today, Prineha Narang will tell us about the quantum internet and how that is getting started. Please take it away, Prineha.
Absolutely. All right. So thank you all for having me here. It is a great privilege to present here, to have a chance to share our work. And thank you again to Womanium for inviting me. I was just learning about the organization. Okay, I don't know if you were able to see my screen share. I guess that's the part I'm now concerned about. This was just working. It's always a second. That is the group test if work.
I already see excited comments by participants. So happy to hear her today. Prineha, thank you for being here. Also some good guesses about when the internet was started. It was 1969 that first message was sent. It was supposed to read login, but after sending the first letters, L and O, it crashed. Let's see what the future will be for quantum networks, quantum internet. Your sites look great, Prineha. Please take it away.
Awesome. So once again, thank you for having me here. I'm really, really excited to share some of the work that we're doing. And as I share some of the technology, I also want to weave in, some of the story, the way this came to be, and my personal journey through this field. So for those of you who have been following this field, you might be seeing the word quantum internet everywhere. You might be thinking, what is the quantum internet about? What is a quantum network? Is that the same as the quantum internet? Is this going to somehow supplant our classical internet? Is it going to work in tandem with it? All of these might be questions that you have in mind. And what I'll try and do is in this talk, give you an idea of where quantum networks are today, what they can do, and what they're poised to do in the future. So kind of help you disentangle, pun intended, some of the components that are going into this and clear up some of the popular culture related confusion that appears around quantum networks and spooky action at a distance. One of the things, as I accepted this talk, I said, well, I'll give this presentation more from the standpoint of, my work as a CTO at Aliro. For those of you who are interested in some of the research that happens in my group, I encourage you to look at our website, and there's a whole bunch of research talks that I've recorded, but I felt that would be a little too specialized for this situation. So quantum networks have tremendous opportunity, okay? And I emphasize opportunity because it's not something that you're unlocking, yesterday or today, but something that you're thinking about over the next 3, 5, 10 years. And for primarily students entering the field, that ought to be very exciting because you can see where your work, your contribution could fit in today, 3 years from now, 5, and if you have a really clear crystal ball, even 10 years from now. So there is a spectrum of things you could contribute to that mirror the quantum network opportunities, at least as I see them, right? So the first, and perhaps the one that you hear about most in popular culture, is quantum secure communications. And there is immense amount that has been written about QKD or key distribution. Now, I want to emphasize this, and if there's one thing you walk away from this talk, it should be that key distribution and entanglement generating and sharing networks are not one and the same thing. And in fact, entanglement-based networks can give us more than we would ever be able to get from a standard QKD type network. And I want to further emphasize that some of these QKD networks have been around. There are other companies that have commercialized these over the years, okay? Now, all of this excitement in quantum secure communications really comes from the fact that existing encryption, the way that we think about how your bank data is protected, how when you log in, things are encrypted, all of that relies on classical asymmetric encryption. And there has been a sentiment and some conjectures, and now more recently, even some hints that this encryption might be threatened by quantum computers. Now, whether or not it is threatened by quantum computers, the idea of quantum secure communication stands by itself because we're interested in how we can share data across the world. Okay, we don't have networks that do this across the world yet, okay, but eventually across the world that really are not susceptible to some of the attacks that classical encryption is known to be. Okay, so that's one promise. Now that's not the only thing, right? There's a lot more you can do with a quantum network, and one that gets a little less press than all of them is distributed quantum sensing. And this is an idea where you can think about connecting various quantum networks, quantum sensors, I'm sorry, via a quantum network. And that would allow you to, for example, have these ultra precise clocks, get to a scenario where very, very precise GPS, position, navigation, and timing, and of course, thinking about really, really cool ultra high resolution telescopes. Like many of you, I have been completely in awe of the pictures that we've seen from the James Webb Space Telescope. I looked at some of those and I felt like, oh my gosh, how will I get our fields, or maybe even our work as a microcosm, to a point where it could inspire even a fraction of that kind of thought, right? So there is a pathway to that. It's a longer pathway, but I'd say that some of the work in quantum sensing could allow us to really see very, very low light signals, allow us to look at information differently, particularly when you connect these quantum sensors. So there's work that's happening in distributed quantum sensing. And of course, there are reasons that we want to know what, it's not just for space. We also perhaps could think of applications of such quantum sensors here terrestrially, or even in various marine applications. So there's like a lot here that is of interest. The third and fourth that have some commonality, and perhaps the ones you've been hearing about this week in terms of quantum computing, right? So when you think about how you could get to a larger quantum computer, well, one is, try and put more qubits on the same device, same chip. There's this idea that, we're going to have this monolith kind of device. There's a parallel idea that we're actually going to scale by connecting various chips. Now, as soon as I say that idea, you might be like, yeah, isn't that how we do things classically? Yes, exactly. That is how we do things classically. In fact, we build larger devices by connecting smaller devices. This is something that has allowed us to really scale classical computers in a way that is not limited by thermal management. It's not limited by lithography. There's just a lot more you can do. Now, the challenge, of course, as you start connecting, clustering, or in some way, putting these together, is that you need a fabric, right? Now, classically, there's an existing fabric. We do this in data centers, in fact, and there are various companies that have been successful in creating the fabric, the interconnect fabric at a data center. Now, you can imagine a similar thing happening for quantum networks, except that the challenge is that when you connect quantum devices together, you have to connect them using a quantum network rather than a classical network, which is another very crude way of saying, if I have two quantum devices and I connect them classically, I don't have a bigger quantum device. I have to be able to connect them somehow quantumly. And that is where the idea of clustered and distributed quantum computing come into the picture. You can imagine scenarios where we're thinking of a data center with these large superconducting qubit platforms connected with each other, using a quantum network that uses photons or phonons or some combination thereof. There are ideas on how such a quantum bus, for example, would be put together. You can also think of heterogeneous devices put together, right? So there's no reason why you only need superconducting and superconducting. You can superconducting trapped ion, solid state. And there are advantages because as soon as you can start to do that, you can take the best of your qubit platform. So you can, for example, take the best of long coherence times, you can take the best of fast gates. There's just a lot you can do once you start to connect these. And the reason for doing all of that, besides the fact that it'd be very cool to create some of these large quantum devices, is that this is a pathway to scale. This is where some of those very useful applications of quantum devices actually become available to us. And this is, you've probably heard talks from others in this conference about how quantum computers will enable new materials, drug design, optimization. Well, all of those things go through the path of getting to scale, and the path to scale, in my opinion, and the opinion of many others, actually goes through some way of clustering or distributing these. And this presents an opportunity, not just for hardware, right? Because everything I just described sounds like, well, this is all hardware design and systems engineering. It is, but there's also a lot that you can do from a software standpoint, because as you start to think about these distributed algorithms, there's a tremendous opportunity for how you would realize that, and taking existing algorithms and breaking them down. It's not that simple. I think there's a lot of interesting both quantum software and quantum algorithm design that can be done in this context. Okay, so yeah, that's at a very high level. What are our opportunities? What are things that we could do? How should we think about the landscape? Let me add a little more, concrete information on each of those sub areas and platforms that I just introduced. Okay, and if there are any questions, by the way, ask either on Zoom or Discord, and I believe they'll get relayed to me. So I want to make sure everyone is completely in sync with what we're doing here.
Yes, great. Some very advanced questions already, which we will definitely address at the end. Great. Thank you so much, Juliana, Abba, and others.
Okay. So, when we think about quantum secure communications, and, we're, interested in why, what's the problem, right? So this is something I've learned over time. First, you need to figure out what's the problem we're solving before you say that I have the perfect solution to solve this problem, right? The problem is that many believe, many have shown signs of existing encryption protocols being no longer safe, okay? And this is something that, of course, has been the promise of quantum computers, in addition to optimization, that, you know, at scale, quantum computers will be able to get past asymmetric encryption, RSA, DSA, Diffie-Hellman. I think there's you know, a sentiment that we ought to do something about it. Now, people have very polarizing views on this, and I don't want to get too much into that. But to say that, you know, when there is a risk of that nature, perhaps we ought to think about it for more than you know, a minute. And there are companies out there now that are specializing in this idea of harvest now, decrypt later, when a sufficiently powerful quantum computer exists. And when you look at it through that lens, it starts to appear like a lot of data is at risk. So that's at a very high level the problem. Okay. Now it's a very doom and gloom problem, but I'm not a doom and gloom person, so I'm going to turn this around and say all problems have solutions. And to solve this problem, right, there are folks who are proposing post quantum cryptography, PQC, various kinds of encryption algorithms. I have not worked in that field, but I encourage you to take a look at, you know, some of the work that's happening there and see, you know, how these have been validated. I think this is yet another open question that people have. Are these actually PQC, or are they just, do they just appear to be PQC, or are they beyond today's quantum computers, but certainly not what we expect in, you know, 5 to 10 years. Okay, so PQC is one approach. The other is QKD. This has also been around for a while. It's point to point. There are companies that do this. There are some challenges with that. The biggest one from my, you know, perspective is that it's a single purpose, you know, quantum connect. It's not really a generalized network, right? And when we talk about the internet, what's powerful is that it's a generalized network. It's not just, you know, two points that are tied with each other. And what we're working on at Aliro, by the way, Aliro is not the only company. There's really pioneering work coming out of Delft. There are classical network companies that are now getting into it, Juniper, Cisco, and others. So there's, you know, others that are working on it. I'm of course speaking from my standpoint as the Aliro CTO here today, and saying that, you know, quantum secure communications that rely on quantum networks are that rely on entanglement sharing. Quantum networks are actually quite promising. Now, the other reason to do this, of course, is that the networks that you would realize in that context are universal, so they can be used for other things as well, which has some advantages. Okay, so, you know, use cases are ginormous. You know, when I start to talk about some of the PQC and risk to RSA, people immediately assume it's a government and defense, but what you don't realize is that a lot of our critical infrastructure relies on secure data, banking and finance, how we think about intellectual property, how we think about healthcare related data. You know, there are various different telecom and cloud and data centers that house enormous amounts of very sensitive information, not sensitive in a defense sense, but sensitive in the sense of I wouldn't want you know, some of this to make its way to someone who it wasn't shared with, right? And so that's what makes this an area that is getting a lot of attention. It's also an area where you'll see a lot of noise in the sense that there are solutions being promised that are a subset of what is needed rather than the full solution. Okay, so, you know, what we're thinking of here is something that looks like this cartoon on the left. Right, there's something you could have. You can have various point to point. You could have various buildings connected with each other. You could have various applications. You don't need to. This is what we do when we think about the cloud in our classical sense, right? I'm able to access my data. Say I'm trying to access Dropbox. I can do that while I'm on a flight headed and you know, as long as my airplane internet is working, I can actually access my data basically from anywhere, right? So that's important. Obviously, quantum networks are not at a point where we can do something quite that general, but I think that there is a promise here that once you can establish kind of this backbone of entanglement that's shared across the network, you have the opportunity to set up something that looks like this generalized quantum internet. And then you don't need to know what's happening at every endpoint. You don't care. In fact, it'd be ideal if every endpoint was somewhat independent, and if it went down, there's no impact. That's another way of saying that if the internet is impacted in one location, that does not immediately impact any other locations. Something we take for granted with classical networks, but yet to be realized with a quantum network. Now, I'm taking a few things for granted here that folks are in fact familiar with entanglement, familiar with this idea that we're talking about something that is inherently quantum mechanical. I'll just say the one line that you've probably heard from various people about entanglement. It doesn't have a classical analog. It is something that is truly quantum mechanical, and that is what confers the superpower for such quantum networks. Okay, so and hopefully there were other talks in the school that went over entanglement in a little more detail. So next, I want to switch over to talking about quantum sensing and tell you a little bit about the promise of distributed quantum sensing. And this is an area where you can do very, very sensitive measurements, thinking about gravitational fields. You can do really, really nice magnetometers. There's really, I think, an opportunity here to, for example, now living in California, I think a lot about earthquakes. I think there's an opportunity to use quantum sensors, connected quantum sensors, actually, to detect tremors very, very soon. Early detection, of course, is important in this context. I think about microscopy. With my hat on as a condensed matter physicist, I'd say that the way people are using quantum sensors in even connected quantum sensors in condensed matter is quite remarkable. Is they're using the quantum sensors to learn about materials that have long-range correlations. We and others have done some of this work where you really learn something you would not from a traditional microscopy or scanning a probe technique, from actually using quantum sensors as the reporters of what's happening in this material. So I think this is quite exciting. Of course, there are more commercially robust applications, things in medical imaging, thinking about various types of testing of devices, fiber testing, for example. So you can imagine a scenario where the devices that are being delivered that are considered to be important or critical technologies are somehow validated using quantum sensors. In fact, there are companies that are doing exactly that. Fiber being an example, but you could also think of other semiconductor devices where you're using a similar technique. So, there's, I alluded to the application in telescopes, and of course, thinking about very, very accurate radar. And this is kind of how it would look, right? So it's and by the way, there is really nice published work on these that you should take a look at from Sachin Zhang, who is at the University of Arizona. He does some really nice work in this, and of course some work by Gottesman and others that is highly well respected in long baseline telescopes with quantum repeaters. Now, there's reason to do both of these. And in fact, underlying both of these applications is the idea that you could actually have a robust sharing of entanglement that is using a quantum network. And finally, and this is something that gets people quite excited, thinking about atomic clocks that are connected by quantum network, very, very accurate GPS, very accurate clocks, and just interesting applications that are enabled by a very precise measurement of fundamental constants in physics. So I think this is quite exciting. If there are physicists here in the audience, I encourage you to look at this area. And for us, this just represents another opportunity to think about how we would connect various things in the stack. You could think of a network as having various layers, and to us, those layers look very similar, regardless of whether you're using it for communication or sensing. There are changes at the application level, but when you're thinking about the data management plane, when you think about the control plane, I think that some of the fundamental technology, the technology that we're building at Aliro, is actually very, very similar across those. Okay, so hopefully I'm doing okay on time. So I want to now get to the application that perhaps many of you have heard about, which is in distributed and clustered quantum computing. Now, so much has been written about quantum computing and you know, all the things quantum computing will do for us that we haven't been able to with classical devices. I just want to temper some of that enthusiasm by saying, yes, all of those things might become possible when we have large-scale quantum computers, okay? Not the quantum devices we have today. So these are long-term applications, okay? The problems that we're trying to solve here, you know, the hope is that we'd be able to do it better and faster than classical computers. I doubt that cheaper will be the first driving factor, but okay, I'll leave that one out. And you know, there's some problems that people believe are best done on a quantum computer. Okay, the word impossible is a little scary, so I think there are conjectures, right? That there's some problems that will be solved by quantum computers better than any classical, even biggest, baddest supercomputer could. And there's really a reason for it, right? I think it's because we want to be able to simulate very large complex molecules. And this is a problem where you're essentially taking an inherently quantum problem, and if you try and solve it on a classical computer, you're making some assumptions, right? You're not able to treat the full many-body wave function, the long-range correlations in these molecules explicitly. So when you break down the problem and solve it on a classical supercomputer, you're essentially making approximations that reduce the fidelity of the calculations that you want to do. Having said that, you know, mapping some of these molecules, some of these bigger problems on a quantum computer, today's quantum computers is probably challenging, but we can, again, envision a scenario where it won't be so challenging in future. You know, molecules and materials have a lot in common, some things that they don't have in common, but, you know, in terms of how you think about solving these problems on a quantum computer, you know, the various algorithms, various ansatz that have been introduced, and I think this is where a majority of the field has done work in the past few years. There's an emerging area in quantum machine learning. I think that is a field that, you know, it started with a few people, and now I think it's grown to a subfield of itself within quantum computing. I think the questions that remain to be answered are, you know, what size devices, what are the types of algorithms, and how are we actually seeing something in quantum machine learning that we wouldn't in other contexts. I think that's really, you know, ultimately what the question comes down to is how are we using these devices in a way that we are not able to use classical computers, and that's a hard one to answer. But you know, it's something that various people are thinking about. There's various efforts from people doing financial modeling. You know, you may have heard from various folks in the financial sector as to how they're using quantum computers. I'm not a financial model expert, but you know, some of those papers seem quite interesting. So from a quantum network standpoint, right, when I look at getting to large quantum computers, I think to myself, well, there are two options that people have, right? You could either scale up and you could get more qubits on a single processor. I think that this is going to have some limits. What that limit is, we don't know, but you know, we could say that even in a best case scenario where you can do amazing thermal management, where you can do amazing integration, this might not get us to those, you know, millions of qubits that we're interested in, right? And those numbers, thousands, millions, you know, you can scale them depending on your optimism or skepticism by a factor that is either 10 or 100x or a fractional, right? So that really depends on how optimistic or pessimistic you are. So you can take this as AU, arbitrary units. Okay, but reality remains that scale up will give us some large number of qubits, but not nearly the largest number of qubits that we want. That scale out will give us where we are able to cluster multiple quantum processors. And now when we think about clustering multiple quantum processors, you get to this idea of, you know, well, I need to link these somehow. And if I'm linking them using, say, flying qubits using photons, well, I have a bit of a problem that I need to solve. And this is typically referred to as the quantum transduction challenge, right? So this is where you have a qubit of one modality, you convert it to a flying qubit, say, you go from solid state to photon, and then from photon, you want to go back to solid state, okay? And what you want to do is you don't want information loss in this, because otherwise it's not really going to come together as a bigger quantum computer. And you also don't want this to be such a resource heavy or, pardon me, onerous process that it, essentially ends up being decoupled quantum devices that would essentially take away from the scale up capability. So now, towards solving this transaction challenge, I and others have written, a whole bunch of papers around this. Really, really nice work coming out of the University of Chicago. Really nice work coming out of Berkeley on this topic as well, where folks are thinking of what would be the ideal quantum bus, right? Like what would be the best way of connecting some of these devices? Is photons the only way? Can you use phonons or optic mechanics? There's some nice ideas in that. Could you use other collective excitations like magnons to do that? I think there's a lot of fundamental science to be done here that then immediately translates into something that is technologically relevant. Something that the field is very cognizant of now, and I appreciate that, is the fabrication challenges associated with such transaction schemes. So what I mean by that is that people are thinking now already from day zero, which of the technologies is going to be more compatible with, say, a large scale fab. And this is something we've seen from Intel and others in their announcements that instead of solving that problem secondarily, they're thinking about it as a primary challenge. And I think that bodes well for this becoming a technology in the near future. So finally, how does this evolve? So previous work was point-to-point, networks, point-to-point, that connect point A, point B, point C, and that's it. Now we're at a point where we can start to talk about clustered endpoints. We can talk about a few of them connected. They can talk to each other pairwise. They can talk maybe in clusters of 3. There's really a little bit of this that is happening. Now, what's missing that I've alluded to but not really touched on in too much detail is a quantum repeater. This is a very poorly named piece of tech in some ways, because when I say repeater, you think, oh no, but that would violate the no cloning theorem that I learned about. We're not violating the no cloning theorem. When you think about a repeater, you're really essentially performing a swap operation. So you're not really repeating the data the same way you would in classical, say, architecture where you're amplifying a signal. So in a quantum repeater, something fundamentally different is happening. I have a completely different talk I give on quantum repeaters. We in our group work on how, actually supported by an NSF Career Award, you've been thinking about how you can get to next generation quantum repeaters that are inherently more robust and can be integrated. And so we call them, third generation repeaters, and there's some work in that domain happening theoretically in my group, experimentally in other groups. Now, once those repeaters come to life, you can think about creating a chain. You can think about a more complex network where there are pieces here that are repeaters of things that are allowing the network to exist. There are also pieces here that are using the entanglement, right? And this is where you start to think of the entanglement essentially as being a backbone. You can think of cute phrases like entanglement as a service that it can enter, and it's being shared with endpoint or midpoint devices that could be computers, that could be used for communication, or that could be used for sensing. And finally, this is what an eventual internet architecture could look like, right? So a few things that we take for granted for quantum internet, that for classical internet that we need to figure out for quantum internet are the repeaters, so these long distances, right? We need a repeater to actually get to distances that are beyond the repeater that's bound, which really would limit us to metropolitan areas. So even to get to a network that is across the East and West Coast, we would need many, many repeaters. The various pieces of the stack from a software and control standpoint that need to be developed, how much of the synchronization, right? So immediately when I talk about devices that are spread out quite far, you realize, well, am I going to need to synchronize these very precisely? Well, you think about how many problems you do as hard real-time synchronization, how many you do as something that can be absorbed into the software, right? We don't think about hard real-time synchronization whatsoever for say classical computing at the moment. And that distinguishes some of the long-range networks from some of the work happening in, say, data center type scenarios where you could brute force some of these problems a lot more. So as I'm saying all of this, right, things you should take away is if I'm an electrical engineer and I've taken a networking course. Well, how could I perhaps link some of that work with quantum networking, right? And I think there's an opportunity there. If you're a systems design person, this ought to be a very exciting system for you, because you're thinking, wow, there's so many little components, how they talk to each other, how they come together. This is really a systems design problem in some ways, where you can parameterize your larger model with the components that go in, but then that gives you some tolerances for where and what each of those individual components ought to be doing. It's obvious if you're working in software that there's a spot for you in this field, whether it's on algorithms, whether it's on controlled software. Pardon me. There's of course an opportunity for those of you who are interested in mathematical aspects of those algorithms. I think there's still a lot to be done. And very, very importantly, I think there's a tremendous untapped opportunity for folks who are coming from a hardware standpoint. And I don't just mean hardware in the quantum hardware context, of course, that's very, very important here. But there's so much here that is related to classical optics, or maybe not just classical optics, but just optics. There's so much here that's related to circuit design, things that are related to microwave engineering. So I think if those are disciplines that you've thought about, particularly if you're an early undergraduate student, I encourage you to take a deeper look and figure out how you can be part of the quantum internet. Now's the time to start thinking about those things, because I suspect that by the time you start graduating from college, graduating from your PhD or master's degrees, these fields will be growing even more. I think all of these fields working on various parts of this problem are hiring quite aggressively. And I just want to leave this up here, that if you're interested in working on quantum networks, you should also perhaps think about working at Aliro. So with that, I'm going to stop. I was told I have about 35 minutes, then we want to leave time for questions. So I'm going to open the floor here for questions.
Fantastic. Thank you so much, Prineha. A wonderful overview over the whole field. Also great encouragement for everyone to join. There are many questions, some looking forward, some clarifying, some you already answered. One of them is, you told about a lot of things, quantum sensing, quantum secure communication, quantum internet. What is Aliro's value proposition? A startup company cannot do everything at the same time.
Sure. So excellent question. And I'm glad that somebody asked. Aliro is focused on so I alluded to the layers of a quantum network that are general across these applications. And we're building out, the data management plane, the control plane. These are, things that you would recognize as, if you're familiar with the layers of a classical network, these are the lower level layers that talk down to the metal, but also talk up to the application layer. Yeah. And, for those of you who are very, very astute in this field, you might be saying, aha, some of this sounds like SDN. Yes, there is a little bit of quantum SDN that we do at Aliro. And we're thinking about actually what are the limitations of SDN that we can overcome when we are designing, the quantum networks for the future. Because even classically, people are saying that SDN is a little bit old. Yeah. So that was an excellent question. I didn't want to take this public forum to tell you and pitch you on Aliro necessarily, but whoever that question came from, I'm happy to dive into great detail as to why the layers of a network would involve the Aliro tech. Yeah.
Wonderful. Abba Naik asks, the approach and uses of distributed quantum computing and the AWS service to provide quantum computer through cloud sounds pretty similar to me. What is the difference?
Yeah, so excellent question. And let's put it this way, right? So when you think about AWS, when you think about the cloud, you're inherently thinking about something that is classical at the moment, right? You don't have a quantum internet that is coming to your home. If you ask your service provider, I want entanglement as a service delivered to my home, they would look at you funny and say, you want what? So what that means is you are taking something that is a quantum problem, you're sending it over to AWS, you're using that quantum computer to work on the problem, and it's being sent back to you classically, okay? That prevents you from doing anything that resembles, say, blind quantum computing. It's preventing you from actually using even multiple AWS devices that are connected to each other quantum mechanically. This is a point I made perhaps a little subtly, so let me say it again. If I have two quantum computers and I connect them classically, I do not have a bigger quantum device, and I'm not able to actually run a quantum algorithm across them like I did. Okay, so that at that point, I'm just taking a problem, using a classical control to break it down, and using that approach. So hopefully that answered your question. If it didn't, I'm happy to elaborate on this a lot more. Yeah.
Very clear. Thank you. Shorya Agrawal, USA asks, how long do you think it will take to get to third-generation quantum networks with full quantum error correction without classical signaling, or is that even possible?
Okay, so I'll answer the last part of that and say, yes, it's possible. There's no fundamental bound that prevents us from getting there. In the true words of a theorist, I'd say prediction is hard, especially about the future, especially when it comes to time scales. I think that there are various roadmaps people have put forward. There's a very nice roadmap from Stephanie Weiner that projects how many years or out we would expect to see such error-corrected networks. I'd take a conservative guess and say, within the next decade, we should start to see some of these error-corrected networks. And I know this is a recorded talk, so someone somewhere a decade from now will play this clip to me and say, you made a prediction, but you asked me, and that's the prediction I think that makes sense today.
Great. Then Louis, also from USA, asks, will all future networks be quantum or hybrid, or will having both classical and quantum networks be convenient?
Sure. Okay, so that's an excellent question. And the way to think about it is that quantum networks are not replacing classical networks. They're satisfying a different use that current classical networks cannot, right? But with all of these, we're talking about using existing telecom fiber, right? And that's something that is quite important because we're not talking about entirely new wavelength ranges, entirely new fiber. The idea would be that we're somehow leveraging existing fiber in the ground. And in order to do that, we ought to then think about how would this coexist with a classical network. And there are approaches to do that, particularly by colleagues at Brookhaven National Lab, where they're really thinking about this hybrid design quite explicitly. Yeah, most of the lab experiments have been done assuming that all your fiber school is doing is the quantum network part, right? But in reality, the promise people put forward is that we're doing this at telecom, so existing fiber should work. And in order to do that, you need to actually see how it coexists. Yeah.
Could you tell more about these current experiments? Yining asks, what is the farthest distance between entangled quantum in the quantum communication via a satellite so far? Has it been checked and confirmed that gravity does not interfere with the entanglement in this or any other distances via satellite?
Yeah, so there is, work that has shown how folks can do this, not just terrestrially, but using satellite-based platforms. There've been, announcements by folks from the UK. There's a company based in the UK that's doing this explicitly. There are companies and entities based in China that have made, various demonstrations. I think there's a lot of debate when it comes to distance because the question really is, what are you distributing over that distance? If you're just doing key distribution, that's important, but it's not getting to this entanglement generating sharing network. And, that then precludes me from answering your question of, what is the impact of all these other factors that enter when you're using satellite-based platforms. But there's a lot of work, there's a lot of interest in how you can put these on satellites, how you can even put them on satellites, so smaller platforms, right? So not the giant satellites, but things that, and I think you could see a nice synergy between, various space-based platforms where people are talking about connecting these various satellites already with a photonic kind of fabric, right? That's something that various companies that show up in popular culture a lot are doing already. So if you can go and change your QuBiT modality into a photon, then suddenly you already have a fabric that exists in space. So I think there's tremendous opportunity. And I think you would now ask the question, if I did all of that, what would it be useful for? And who would be the first customer? And as a company, we've been asking ourselves that question and thinking about, exactly what does that first customer want in the next, year, 2 years before we worry about this really, really cool tech. I, of course, want all of this really cool tech to be realized as quickly as possible, but I think we also need to prioritize in terms of what our customers want delivered first.
Wonderful. Then a more physics question, Shoria USA. How exactly are you using entanglement swapping and other techniques to optimize transfer of information?
Yeah, so the idea of a repeater, right? That's where the swap operation is happening. You could think about doing this in, using a matter-based, and by matter-based, I really, from my perspective, mean a solid-state material-based repeater scheme, either using color centers in diamond or silicon carbide, and that's where you're, essentially thinking about going from photon to matter-based, and then back to photon. That's where that transduction problem also comes into play. A repeater doesn't just have to be based on solid state. In fact, there are companies that are doing this now based on, AMO platforms. There's nice work by Eden Figueroa and others showing that actually you could do this warm gas-based repeater scheme that could, essentially operate pretty close to room temperature. Of course, when he's saying repeater, he's not talking about repeater. He's talking about a larger laser table that probably spans from wall to wall in where I'm standing. So it's not a rack-mounted repeater yet. I think we'll get to a point where we're talking about rack-mounted repeaters, either based in solid state or based on some of these other AMO platforms, perhaps based on all of the above, where you can perform very, very efficient swap operations, and you get a choice of which one you use based on some other end application, right? When we think about this classically, I don't know what's in a rack in some, run by some telecom company. And the importance of all of this is that as a company that is interested in working on these platforms without getting tied to a single platform, we want to actually not specialize the entire stack to a particular repeater scheme, because that would be both technologically and from a business standpoint a bad idea.
Yeah. There are some visionary entrepreneurs here who want to time travel in future using quantum networks. But let me go to the next question from Alex in Thailand. What are some of the key challenges faced as a quantum computing startup, or generally quantum startup, during the investment, funding, and IPO process? Or maybe generally about your entrepreneurial journey?
Yeah, I think when people say what are challenges, I could have a long laundry list, but I'll just pick like the top few. So as an early stage startup, particularly one that came out of an academic context, I think the question of, well, how are you going to monetize this came up a lot. And we're presenting technology that is very exciting, very futuristic, but I think the question that people want an answer to is, how are you going to say make money, to be blunt, in the next, with the milestones that you're putting forward. And I think the way I've approached this is to, be very, very honest about where the current tech is, who the first few customers are, and what we think their problems are, and how we're going to actually work with them to make sure we're solving their problems. I think this is something that, as an early stage startup, it's very tempting to say, well, I have cool tech, and all I have to do is tell people how cool the tech is. But if it's not solving a problem, that's going to be really, really hard to convince people that cool tech ought to be something that's adopted outside a dinner table conversation. The way that we've structured our pitch deck and just in general converse with people is around being candid where the tech is and where the tech is going, and at what point we start to see general adoption beyond say our first 10 customers. So that's one of the challenges. I think the other challenge that we face is when we present information at a high level, for example, the kind of question that came up about how is that different from AWS cloud, we'll telling people that the classical cloud-based platforms are very different from how you think about connecting quantum devices over a quantum internet. Somebody who is fully paying attention may immediately follow that and say, oh yeah, I got it, which I assume happened with the person who asked that question. But when you're pitching this to say somebody who's hearing about cool tech from 8 a.m. to 8 p.m., it might be hard to overcome that threshold of like, how is what you're doing different from all these other acronyms? And if you think about the quantum landscape of various companies, there are so many different announcements every day. I'm in the field, and I think I feel completely overwhelmed when I look at all the pings. Have you seen this? Did you hear about this? It's like, no, I didn't. I just got home from a run this morning. I'll take a look at it. So I think you really have to rise above the noise and realize that once you're committed to a particular pathway, a particular set of customers, and a particular plan, you can't rubberneck as much as you could in science. In science, in my research lab, we're working on something, and then a really cool paper pops up on the archive. We take a look at it and think, oh, how can we either say something about it? Is there something we can incorporate? How does this impact our existing research? You can't necessarily do that as much in a startup. Yeah.
Can you tell more about that part of your professional life? Because Aliro Quantum is only one part. The other big part is being a computational condensed matter physicist.
That's right. So my day job, as it were, is as a theoretical and a computational scientist. And a lot of what my group does is think about materials where the quantum behavior dominates above all else, right? So we call these quantum materials, and the idea is how can we actually predict these quantum materials, predict interactions in these quantum materials, and from a computational standpoint, how can we learn about these properties in a way that we can propose technological uses of these systems. And that could be in the context of these color centers that are relevant for repeater schemes. That could be in the context of various correlations in these for dissipation-less nanoelectronics. We've been looking at various types of transport phenomena, and of course other correlated phases that have no classical analog. How do we find and realize these non-equilibrium phases? And this, by the way, the word non-equilibrium quite simply is if you're taking something and pushing it out of its comfort zone so far that it doesn't resemble its ground state, how do you start to describe its behavior? How do you start to use some of that non-equilibrium nature of matter? So that's something that we do a lot of in my group. And we are also hiring a bunch of postdocs. So if you work in any of these fields and any of what I said sounded interesting, please write me right away.
And will that be at UCLA or Harvard or both?
Yes. In fact, so I've been, and this was alluded to earlier, there's a little bit of a human superposition aspect here, but I've been leading some of the quantum efforts here at UCLA, and I welcome applications from people. I can put in my contact information into the chat if that's helpful.
That would be fantastic. There are also already people who want to intern for you at Aliro Quantum.
That is phenomenal. I think you can also absolutely write me about that. So there are various ways to contact me, and all of these are completely valid ways, or you can even write they all end up in the same inbox. There you go.
Could you tell more about your journey through academia and then startup, and both?
Sure.
Also in a superposition.
Okay. Well, so I think I've kind of mentioned this before. I got into science physics because I was drawn to how we can think about these problems without being constrained, and really I wanted to be originally an experimentalist. I got to Caltech as a graduate student and started working on a couple of projects, and immediately realized that I'm interested in theory a lot more than some of the experimental aspects. And so I was starting to do these calculations, primarily initially pen and paper, thinking about various things in quantum optics, quantum plasmonics. Started to incorporate things like large GPU architectures into my calculations, and that really helped. I went on to do a brief postdoc at MIT, and then I started in the faculty at Harvard, and now, of course, being a senior faculty member here at UCLA. So that's been a little bit of my journey. through all of these, steps, I've kind of thought about, what's the problem we're solving. So my research has definitely kind of, grown. It's taken a nonlinear path through time, and I think that's really what makes research really fun. Aliro was a complete surprise. So there were, students in my group who were working on the topics that became the initial kind of team of Aliro, and they were really interested in being entrepreneurs. They were really interested in how could we realize and bring this technology to life. And we working together with the tech transfer office at Harvard and working together with some of the Boston-based VCs, were able to very quickly raise a round. We originally felt that, okay, we should focus on quantum software very broadly. Immediately realized that actually focusing on quantum network software is where our strength really lies. For those of you who are not familiar, Boston has a very strong classical networking tradition, many companies, Arista 128, there's just like a lot happening. And we also rapidly realized that we have a strength in merging classical and quantum networking, so kind of bringing those two communities together, and that's not something you could easily do in a research context. So from there, raised another round, and we've now grown to a team of about 20 people. And we're looking to nearly double that team. So if you're interested, again, please write us. Yeah.
What is your ultimate advice for the participants to leverage their potential in careers, quantum careers?
I think
their quantum
the
journey.
biggest piece of advice is that, keep your eyes open for some of the opportunities that are coming in, some of the tech that, people are trying to scale, the tech that people are trying to commercialize, especially if you're interested in the entrepreneurial aspect. Maybe you started in quantum computing. Don't think, well, that means I am precluded from working on quantum networking or quantum sensing or some other new quantum application that's become available, because you'd be amazed at how transferable the skills are across this entire domain. And they're certainly much more transferable across this domain than, say, people coming with no quantum background. So that's I think my general advice is follow where you think you're seeing the coolest tech.
That is great advice. Thank you so much for this fantastic presentation. Great insights, great answers to questions, which people are already thanking you for. Looking forward to continuing the conversation another time, also involving the participants there. And Prachi is popping up too for some final words. Thank you so much, Prineha. Very happy to have had you here today.
Awesome. Thank you so much.
Okay. And then the next talk will be given by Clarice Aiello. Yes, and you are joining also from Los Angeles at the moment. Prineha and Clarice are both in, well, Prineha will soon be at UCLA. Clarice is there right now. So wonderful session. Thank you again, Prineha. Broad insight. And now we will move to another type of quantum. We will actually continue the quantum sensing, but we will look how living creatures can be living quantum sensors, not at cryogenic temperatures that we learned about last week and this week, but at room temperature, as we are all now in these noisy environments. Clarice is a professor at UCLA, where she leads the QuBiT Lab. In this case, it stands for Quantum, Bio, and Tech, where she unites all these three. Previously, she held positions at Berkeley, Stanford, if I am right, and a PhD from MIT. She is a quantum engineer looking how quantum physics informs biology. And we are very curious for your talk, Clarice. Welcome to the group. And everyone, be ready to ask so many questions again on Discord. Final words to Prineha. I see she's still here. Many thank you on the Discord for the amazing presentation and interesting lecture and wonderful talk. Now, getting started, Clarice, please take it away.
I am so, can you hear me well? Or is my voice okay?
Yes, and Lindsay, if you want to comment on it, you are our good tester. Is the audio good? Is the video good?
1,
The
2,
slides?
3, 1, 2, 3.
Yep, you're all
Okay,
set.
good to go. Awesome. So I'm super happy to be here, and I'm truly looking forward to discussing with you all later on. So I like to call myself a quantum engineer, right? So this means that I build apparatuses to study and control things that are so small and so well protected from their environment that they're better described by the laws of quantum mechanics, as opposed to the laws of classical mechanics that rule everything big around us. So people, wait, why can't I move? Oh. So people get a little bit confused when I say that in our group, we study things that might be going on inside birds and butterflies. So before I explain where I'm going, I really need to tell you where I come from. So we're going to start this talk by talking about hardcore quantum mechanics, technological quantum sensing, and by the end of the hour, we will have talked about things of biological relevance, such as how organisms migrate, how our cells respond to oxidative stress, how our cells respond to radiation, and I hope I will have instilled in you the curiosity to learn more about how I think we can learn with nature how to build better technologies. And that's because I'm a quantum engineer who's interested in how quantum physics informs biology at the nanoscale. So I usually start this talk by saying that I believe humankind is obsessed with measuring things better because this means that we understand them better. For example, we might think about measuring better frequencies or better time chunks. This picture there is from an atomic clock that sits at NIST here in the US. And based on an atomic transition, it helps us define extremely precisely what a second or what a hertz is. We can think about measuring better magnetic fields so that the image of your baby is better resolved. For example, this, yes, is the magnetic resonance image of a baby inside the mother's belly. Or we can think about measuring better accelerations with those tiny little accelerometers so that your, gaming,
For us, it still looks good. There we go.
So that your gaming experience is enhanced. Those tiny little accelerometers, nanofabricated accelerometers, are now ubiquitous in all our handheld devices. But the question that I ask is, what happens if the quantity that you want to measure is very, very small? Or worse, what happens if the object that causes the quantity that you want to measure is very, very small? I'm going to argue that in this case, you need a tiny little sensor that can be brought in very close proximity to this tiny little object producing tiny little quantities. If the sensor is tiny, let's make it very tiny. Let's make it quantum. And actually, there's a whole body of mathematical arguments that you can use to prove that if you use a quantum object as a sensor, your measurement is improved. In other words, the sensor quantumness enhances the measurement. In my past, I worked with a single electronic spin in diamond, in the material diamond, and that I could put to use as a very good magnetic field sensor, quantum enhanced magnetic field sensor. So I would like to spend some time talking about this technological quantum sensor. And truth be told, I'm going to do this for a reason. I'm going to do this because I'm going to show to you how similar this technological quantum sensor is to some ways that biological materials are using to interact with their environment. So, but let's talk about this technological quantum sensor first. So here's the promise. A single spinning diamond can be put to use as a very good magnetic field sensor. So just as a recap, spin is a merely quantum degree of freedom, right? It doesn't have a classical equivalent, and it measures how well an object, a quantum object, interacts with a magnetic field. Spin is as fundamental as charge and mass. And if you think about it, you know, like things that we take for granted, like the concept of charge, right? The concept of charge is something that tells you how well an object interacts with electric fields. And it's really crazy because charge is a construction that we use to understand how objects interact with electric fields. Spin is the same. Spin is a quantum mechanical property, a construct, if you will, that helps us understand how objects interact with magnetic fields. So a spin is usually denoted with an arrow, say spin up or spin down, which represent two different energy levels of this interaction of the object with magnetic fields. So, but the electronic spin that I worked with existed in diamond, in the material diamond. And in fact, it arose from a crystalline defect in the diamond lattice. Okay, so this crystalline defect actually belongs to a class of crystalline defects that are referred to as color centers. Color centers are called this way because they have the very interesting property that they absorb light, get excited, and then they emit light back. They fluoresce. Color centers are the crystalline defect that are responsible for the colors of the diamonds that you see there at the bottom of the picture. The particular crystalline defect that I worked with is a very famous crystalline defect known as the nitrogen vacancy center. It arises naturally, but it can also be engineered, and it happens when a vacancy, that is a missing carbon atom in the diamond lattice, sits nearby to a nitrogen, that is the most naturally occurring substitutional impurity in the diamond lattice. Okay, so a nitrogen sits together to missing carbon atoms. Actually, if you look about it, what happens around this defect is a bit of an electronic mess, right? The carbons close to the vacancy have unpaired electrons. The nitrogen might be providing extra electrons. There might be charges nearby in the material. It turns out that almost like magic, if we start calculating the energy, the quantum mechanical energy levels of this electronic mess that is localized there, something almost magic happens. And in fact, the quantum mechanical energy levels of this compound really look like the quantum mechanical energy levels of a single electronic spin. So it's actually very convenient because instead of looking at this electronic mass, you can look at it and take it as a single effective electronic spin. It's as if it were, because it is, a single trapped electron spin, okay, that is there, doesn't move. And the way that we actually find and play with those defects in the lab is actually quite simple. Again, everything at room temperature, no vacuum required. And actually, even though people can now engineer those defects, it occurs naturally in nature. And in fact, the very first diamond material that I worked with was a discard from a jeweler. And here's how we found those defects in diamond. You put your diamond slab, your tiny diamond slab, on top of a moving stage, and you move it around at the same time that you shine laser light at this defect. In fact, it doesn't need to be laser light. It's just more efficient and more convenient to do this in the lab. You shine laser light, and the expectation is that as you're moving your diamond slab around, at the time where the laser hits one of those defects, it's a color center, so it will absorb the laser light, get excited, and then de-excite by emitting light, by fluorescing. This fluorescence we can collect and analyze. So here's what this image looks like at increasing zooms. Okay, so for example, in the middle picture there, you see many bright spots, each one corresponding to one single nitrogen vacancy defect. And to the bottom right here, you see a single blob, which, if you think about it, it's quite remarkable because this blob is actually denoting the fluorescence of a single electron spin. If you have heard a little bit about magnetic resonance, that also can get signals from spins. In magnetic resonance, you need a gazillion spins to have any measurable signal. Here, looking at the fluorescence of the single spin, you can actually have access to, like, you can image a single electronic spin, which is amazing, which is quite unusual. But again, it gets even better because for reasons that I won't have time to explain, this defect has what's known as a quantum state dependence fluorescence intensity. This means that just by looking at how strongly this blob is fluorescing, is emitting light, we can actually infer if the state of the spin is up or down. And actually, this is going to be very convenient. It's very convenient to do, and you're probably familiar now with this nomenclature, to do quantum state detection just by looking at fluorescence intensities. But here's the promise that we can put this to use as a quantum enhanced magnetometer. And here how this works. There I draw two things called 0 and 1, which corresponds more or less to like electron energy up, spin up, or spin down. In this vertical axis here, you can understand it as energy. And the difference in energy between spin up and spin down states are in this energy difference is in the microwave range. It's about 3 gigahertz. Okay, and it turns out that the state that I mark as there as 0 is insensitive to magnetic fields. That is, in the presence, if the diamond slab is immersed into a magnetic field, state 0 will not here. However, state marked +1 is sensitive to magnetic fields. This means that if the diamond is immersed in a magnetic field, this state will get promoted to another energy level, will be shifted by a tiny quantity called delta. And it turns out that this delta, by something called the Zeeman interaction, is proportional to the magnetic field strength. So now, if you're not paying attention, this is the time to come back to pay attention, because what I'm going to do now is to explain something that often goes unnoticed. This is basically how 95% of all quantum enhanced sensing works. Okay, listen to this. Because this delta is proportional, this shift in energy is proportional to the magnetic field strength, the problem of measuring magnetic field and magnetic field strength is actually mapped into the problem of being able to measure a mismatch delta from a known energy difference, an energy difference in the absence of magnetic fields. Again, this is how 95% of quantum enhanced sensing works. You have a certain quantity that causes an energy shift, and if the experimentalist is able to measure this energy shift, you are able to measure the quantity that your sensor is immersed in. And luckily, measuring shifts from known resonances, from known energy differences, is a signal processing problem, and that's something that physicists and engineers have known how to do for many, many decades. Okay. So here's how this works as a quantum enhanced magnetic field sensor. For reasons that I also won't have time to explain, this only works while the spin is well described by the properties of quantum mechanics. Everything that starts quantum dies classical, right? As quantum mechanical objects start interacting among themselves and interacting with the environment, they lose their quantum character. So this quantum enhanced sensing protocol can only be useful while the spin is quantum. I think that many of you now are familiar with some of this nomenclature. This means this can only be used while there is a good phase relationship when the spin is in a superposition of, in this case, 0 and 1, while the spin can be put in a superposition of 0 and 1. And for naturally occurring diamonds, again, it can be engineered to be better, but in naturally occurring diamonds, this coherence time is about 2 microseconds at room temperature and in bulk within the carbon lattice. And it turns out, if you have heard about other quantum systems, 2 microseconds is extremely long. Okay, it's extremely long for something quantum to live at room temperature and in bulk, and nature made it this way. Again, as I was sort of motivating here, you know, the longer this coherence times are, the longer this spin remains in a quantum state, the longer you can play with it. You can use it as a quantum sensor. So again, signal processing, right? You take a signal that you get from your sensor as a function of time. The longer the signal is going on without dying out, when you Fourier transform the signal, the better your frequency resolution is going to be. So the idea here is are there things that we can do with the sensor so that we can kick it to keep its quantum character going on and on for longer and longer? And again, this is something that has been known for many, many decades from the field of from the beginnings of magnetic resonance and quantum control. Qubits within matter can be controlled with electromagnetic fields. Just a parenthesis, if you have heard about photonic qubits can be controlled with matter. But here, matter qubits can be controlled with electromagnetic fields. And the idea is that, you know, it's the same thing as if you have a swing, right? If you apply kicks to the swing at particular intervals in time, you can keep the swing going, right? Here, the idea is the same. If we apply carefully electromagnetic kicks to this spin, there's a chance that we can keep it going. We can keep its quantum character going for longer and longer so that we can acquire the signal for longer and longer. So I would like to show you one example of such quantum control, of such controlled electromagnetic kicks. Okay, this is going to be the most technical slide in my presentation. So don't forget the big picture. The big picture is this: having a tiny little sensor that you bring in close proximity to a tiny little sample and that can measure tiny little quantities. Don't forget this. That's the most important thing. Let's go for the one example of such a spin control experiment. So in my past, for example, I kicked this spin in diamonds so that it could be put to use as a very good magnetic field sensor using an electromagnetic sequence that is known as rotary echo. This electromagnetic kick sequence is depicted to the right in magnetic resonance jargon. Here's what this means. This means that I am applying a microwave frequency. I have a microwave cable. I'm bringing this microwave cable in close proximity to the diamond, and I'm applying a frequency that is continuous, that is tuned to the original frequency without the detuning delta between spin up and spin down. And this microwave field is continuous, it's always on, but at certain times that the experimenter can choose, I am actually changing the phase of the microwave pulse. I'm just flipping the phase, always continuous, but with phase flipped. Okay, this is an electromagnetic excitation that has been known from nuclear magnetic resonance for half a century now, and it's known to be able to correct for driving field imperfections. People use this to correct for imperfections in your microwave source. It's also known not to correct for detunings in your for mismatches in your resonance, not to correct for the effects of such detunings from your resonance. And if you remember from my last slide, detunings or mismatches from the resonance is exactly what's going to give you magnetometry, magnetic field information. Okay? So that's a good thing. We're using the right sequence for that. I won't have time to explain, but the interval of time between phase flips can actually be chosen, and by choosing this interval in different ways, you can actually show that you can correct for different decohering, for different noises that the diamond is immersed into. But if you apply then this microwave pulse to the diamond and then capture the signal, here's what you get. This is the signal obtained by nitrogen from the electronic spin. The signal is just fluorescence intensity, right? It's just a fluorescence intensity as a function of the time during which I apply this microwave frequency. It's just this normalized fluorescence intensity. If you remember, differences in fluorescence intensity mean that the spin is up or down. So here, for example, at the top of the signal, you can understand it as the spin being up. At the bottom of the signal, you can understand it as the spin being down. And every fluorescence intensity in between signals a coherent superposition of the spin up and down. For those of you who are familiar with this, this is just a glorified, a modulated Rabi experiment. Okay, this is modulated Rabi signal that you're looking at. So you can apply a mathematical formalism known as average Hamiltonian theory and actually calculate from first principles how this signal depends on this tiny delta. Remember the delta, this shift in your resonance frequency, how the signal is dependent on this delta that you want to measure. And if you know how it depends on delta, you know what magnetic field generates this delta. So using this formula and Fourier transforming this signal, you can actually get to something that is basically, I'm not telling you how to read this, it's basically a spectrum, right? And there are ways that you can read those spectral lines and actually infer what the magnetic field that the diamond is subject to. And in this experiment, we're measuring the NV center, the spin diamond is measuring 3 magnetic fields, the smallest of which is about 1/10 of the magnetic field of the Earth. Again, this is just one example of how this works in the lab, right? But the big picture is that you have small sensor sensing small quantities, right? So this end up the part that I'm going to talk to you about technological quantum sensors. But mind, please, that I've just shown you a quantum sensor, right, that works at room temperature and in noisy environments, in the noisy environment of the diamond and in the of the sample that you're close to. Before I continue, I'm going to maybe share with you one of the things that people often ask me. Okay, so this diamond is immersed within room temperature in principle. It works at room temperature. And this sensor itself has an energy difference of about 3 gigahertz. We don't have time to do this exercise, but then I ask people, so how many gigahertz is KBT at room temperature? And if you had time to Google, you would find out that KBT at room temperature would correspond to an energy of a frequency of about 6,000 gigahertz. Look at what I'm saying. I'm saying that there is this material, this diamond, that is immersed in a thermal bath of about 6,000 gigahertz. And there's this sensor that has a energy difference of only 3 gigahertz. And I'm freaking telling you that this sensor is actually quantum, right? While immersed in this thermal bath. How is it possible that this even makes sense? The energy difference of the sensor is so much smaller than the energy difference of the energy available in the thermal bath. Isn't there a problem there? Isn't there like thermalization? We're not going to have time to talk about it, but the important idea here is that yes, there is thermalization, right? And the important part is that this sensor only works well as a quantum sensor before it thermalizes with the environment, before it loses its quantum character, right? So yes, there is thermalization, but we only care about the quantum properties of this sensor before thermalization kicks in. Again, everything that starts quantum dies classical. So it's just before that time kicks in that we can obtain enhanced quantum information from this sensor. So this is not a paradox at all. So I would like now to shift gears a bit, but not too much. You're going to see why. And again, up to like 5 years ago, you know, I was used to dealing with this type of sensors that you see there. Some quantum enhanced, some not, some classical, but those were all humankind made sensors. And it turns out that at some point I realized that nature many times makes sensors that crazily overperform humankind made sensors in absolute innovative ways. I would like to talk to you about a natural magnetic field sensor that I'm going to argue works in an uncannily similar way to the way that the sensor in diamond is working, okay? But in order for me to talk about biology at the nanoscale, I'm actually going to have to talk about the biology at the nanoscale, namely the chemistry. So it turns out that for decades now, in a field that is known as radical chemistry, it's been known without any doubt for molecules in solution that there is a class of chemical reactions that are spin dependent, which means, in a way that I'm going to show you schematically in a second, that magnetic fields can alter the final products of this class of chemical reactions that depend on spin. Here's basically how it's known to work in chemistry. Okay, no doubt that this is what's happening in the chemistry of molecules in solution. There's a chemical reaction that's happening at some point. The chemical reaction comes to a crossroads, and the chemical reaction effectively looks at the state of a electronic spin. Okay, in fact, it's as if the chemical reaction was performing a quantum measurement and checking the result. If a certain electron spin of interest is up, the chemical reaction continues through one branch. If a certain electron spin is down, the chemical reaction continues through another branch. Importantly, the macroscopic final products of those two branches are different. Now, a brief interaction with the magnetic field as this chemical reaction comes to this crossroads can actually alter the state of the spin, can actually alter the probability of the spin being found in the up or in the down state. It's in this sense that a brief interaction with a magnetic field can actually alter the final products macroscopically of this chemical reaction and at much longer time scales. The interaction is brief, but everything happens downstream. So this has been demonstrated at room temperature in solution in the solid state in the gas phase, and for magnetic fields as weak as the magnetic field of the Earth, which is weaker than the magnetic field that you sense when you put your cell phone close to your face. Okay. Here's what brought what brought this to biology. What brought this type of chemical reaction to biology was birds. I really don't care about birds, and we're going to go away from birds, but birds have the excellent quality that they enabled the discussion to begin. Birds have been known to migrate, again, without a shadow of a doubt. When they migrate, they use the super weak magnetic field of the Earth, at least as a partial cue. There's no doubt that they do this. And people were trying to understand how birds do this. And by the end of the 70s, there was like this brave, crazy biophysicist who proposed the following outrageous at that point hypothesis. Were the same type of spin-sensitive chemical reaction happening physiologically inside the bird somehow, birds and organisms in general could sense magnetic fields to the same extent that they could sense different physiological concentrations of products coming from those branches that could be altered by magnetic fields. So because birds would be able to sense different concentrations of products, they could sense effectively magnetic field and navigate. For example, something that was proposed, never proven or disproven so far, is that there's something that modulates the photosensitivity, the sensitivity to light of the bird inside its retina. So that, say, if a bird looks to one side, the magnetic field is such that certain products modulate the photosensitivity so that it sees with a certain intensity. If a bird looks to another side, there's another magnetic field direction or intensity that sort of modulates the photosensitivity so that birds could maybe really see magnetic field lines. Okay, this was the hypothesis. And at that point, the only known animal, an animal because of birds, protein known to sustain such spin-dependent chemical reactions was a fluorescent protein that is present in the bird's eyes, in the antennas of migrating butterflies, and actually in all our cells, because it also has circadian rhythm circulation functions, was this protein called cryptochrome. And it turns out that cryptochrome is super widespread, its presence throughout the tree of life. organisms from very simple to very complex express cryptochrome. And all those organisms boxed in red there are organisms for which there has been studies macroscopically correlating magnetosensing and cryptochrome. Okay, and actually evidence that cryptochrome works as a quantum enhanced magnetic sensor exists, and there's a lot of it, but it exists at very two disconnected length scales. So to the left in my plot there, you see the very tiny length scales for cryptochromes in solution. For cryptochromes in solution, there is no whatsoever doubt that it is working as a bona fide quantum sensor in ways that I'm going to show you is very similar to the way the nitrogen vacancy center is happening, is sensing magnetic fields. For example, for cryptochromes in solution, and that's the plot to the top left, people measured the fluorescence emitted by this molecule as a function of the time during which you applied a laser to excite that chromophore, that protein. Okay, the first thing that you see is that the fluorescence is going down. This only means that your laser is killing the chromophore, is photo bleaching your sample. It doesn't matter. But as the researchers are capturing this fluorescence, this photo bleaching fluorescence, they also pulse a tiny magnetic field up and down. And again, this is not an artifact. This has been done with several different magnetic field intensities and frequencies. And as the researchers pulse slowly, but they pulse a magnetic field on and off, you see in the inset there that the mean fluorescence intensity emitted also pulses on and off. Again, this is in correlation with what happens in the spin in diamond. Just by looking at how strongly that blob was emitting light, was fluorescing, you could infer if the spin was up or down. Here it's the same thing. Just by looking at how strongly that protein is emitting light, you can actually infer if the spin was measured to be up and the chemical reaction continued through one way, or if the spin was measured to be down and the chemical reaction continued through another way. So this is exactly how you do quantum state detection for those proteins. Moreover, there's evidence, it's not super clear cut, but there's good evidence that seems to indicate that for cryptochromes in solution, that coherence times, the spins can be well described by the laws of quantum mechanics, again, at room temperature in solution for about 1 microsecond, which again is on par with the 2 microseconds that I cited for the naturally occurring diamond. Okay, so that's all very encouraging, except that the next level of evidence occurs macroscopically, and that's those pictures to the right. And they happen for birds, like birds inside cages, flies, plates of cells. So for example, those are beautiful and extremely hard experiments, but they only provide correlative data. For example, during migration season, people grab like 20 birds every year, they put them in cages, and then they mess up. They put them like within coils, and they want to measure where the bird want to get out of the cage to migrate. And by changing the magnetic field, the bird wants to get out through different directions. Flies do not migrate, but they can be trained. I have no idea how they do this. This is more cryptic than quantum mechanics to me. Flies can be trained to find food in the presence of a magnetic field. So they're trained to do this. And then the researchers knock out, that is, remove the cryptochrome gene from the genetics of the flies, and the flies are no longer able to find food in the presence of a magnetic field. In a further experiment, the researchers put back human cryptochrome inside the flies, and the flies are back to being able to find food in the presence of a magnetic field. Plates of cells, like thousands of cells, you put them into a metabolic analyzer. It's some type of mass spec that senses products made by this cell culture. Researchers applied different magnetic fields inside those machines, and they could see changes in the physiological functioning of cells, for example, as far as their glycolysis rates, respiration rates, and acidification rates are concerned. All of this is good, and most of the macroscopic evidence is consistent with the spin mechanism being active under the hood, but there is no unambiguous, proof. There is no experiment that looks at the same time at spin degrees of freedom and physiological happenings. Okay, so and it's very hard to say, well, the bird is doing its thing because somewhere inside the bird there is an obscure spin-dependent chemical reaction happening at room temperature. This is not going to advance the field. So here's what we're starting to do here. In our lab, we're starting to bridge those length scales. This is not my scope. This is the scope that I worked with as a postdoc, but we're building glorified microscopes with coils. We want to bridge those length scales. We want to have an experiment that looks like a quantum sensing experiment, but that acts on biological material. To a physicist, I would describe this as light-matter interactions where matter is biomatter. We want to look at, for example, proteins inside the single cell. Make sure we get to, initialize, manipulate, and read out the spins as you would do with a qubit inside a quantum computer, but we want to do this inside a protein, inside a cell, and then correlate how that might be affecting cellular workings using regular fluorescence microscopy. So we want to look at quantum degrees of freedom and physiology in the same experiment, okay, using this high tech, and this has never been done before. And when I say, oops, that I'm going to build a microscope, it doesn't look like the stuff to the left. It looks like the picture to the right. Again, not our microscope yet. This is just a random picture from an atomic physics lab that I got from the internet. Our experiment is going to look like an atomic physics experiment with plenty of electronics, but acting on a biological sample. And I argue that we need this type of high-tech quantum-inspired instrumentation to treat endogenous quantum mechanical degrees of freedom in biology, right, as if they were, because they are bona fide quantum sensors. Okay, so the cool thing, I won't have time to talk about it, but the cool thing is that differently from many biophysics experiments where people look at things and then model, here we can use a well-established formalism of open quantum systems to actually model what's going on and start making predictions. So for example, for cryptochrome in particular, the bird protein, its photophysics is well established, and we can actually, the simplest model, I mean, even we as experimentalists can perform some these simulations. The minimal model, I won't have time to explain, but it's like 2 electron spins, one of which is hyperfine coupled to another nearby nuclear spin, using 3 spins plus known facts about the photophysics of cryptochrome. We can start making predictions of what exactly is going on. I would like to show you one such prediction. We made this prediction. Other people made this prediction and published before us, but I am dying to take this curve experimentally. So I would like you to look at the top right curve in this slide. There, it's plotted the simulated magnetosensitivity of cryptochrome as a function of magnetic field strengths for cryptochrome in solution, tumbling in solution. What the simulation suggests is interesting. So here's the first thing that the simulation suggests. First of all, this magnetosensitivity curve is not monotonic. It goes up and down. By about 10 times the magnetic field of the Earth, at about 600 microtesla, this magnetosensitivity has decreased by a lot. It's almost 0. This is actually well understood from the spin physics. I won't have time to explain why, but I want to make a point. In their almost entirety, spin-dependent chemical reactions are sensitive to relatively weak magnetic fields, to the magnetic fields on the order of that produced by the Earth, produced by your cell phone. This means that more is not better necessarily. If you put those spin-dependent chemical reactions inside an MRI machine with Tesla magnetic field and slightly change the field, that's not going to have an effect on the spin-dependent chemical reaction for reasons that are well understood, and we can talk about that if we have time. Okay, but this is a consequence. I mean, we can see this in our simulations as well. This is both good and bad, right? Because if spin-dependent chemical reactions depend on weak magnetic fields, this is bad because with weak fields you can, in principle, do bad things, but it's also easy to control things. If we, I'm saying, and I'm going to make this point a little bit later, if we can learn how to deterministically control spin-dependent chemical reactions, we can actually use it maybe in 30 years for therapeutic applications. So this is the first thing that is cool about this prediction plot. The second thing is that this curve of magnetosensitivity, it peaks at very close to the magnetic field of the Earth, okay, which might be a coincidence, or it might be that there has been an evolutionary pressure for the protein that is putatively a sensor of the magnetic field of the Earth to work better for the fields where it's immersed into, right? Again, it's either a coincidence or not. We cannot tell those things apart. We build instruments, but we think that people who do directed evolution of proteins could help us see if there can be evolutionary pressure for the development of such proteins. And again, way to go. If we want to build sensors that can sense a very specific range of magnetic fields, maybe we can learn with nature how to do that. But again, that's another very good time for you to wake up. If you're sleeping, this is not a talk about birds. It would be poor if this were a talk about birds. It's not. There's more correlative evidence that the same type of spin-sensitive chemical reaction that I was talking about might be at play not only for bird migration, but might be at play for a myriad of super relevant physiological phenomena. The production of reactive oxygen species has been shown to be dependent on weak magnetic fields in a way that is consistent with spins. And reactive oxygen species is that stuff that is good for signaling, but if you have too much, it's bad for you. Stem cell growth in planaria has been shown to depend on weak magnetic fields, planaria regeneration, DNA repair in bacteria, autofluorescence of possibly flavoproteins inside mitochondria responds to magnetic field in a way that is spin consistent. But the thing that makes everyone come to my side of the fight to talk about spins in biology is this picture there. So humor me. I have a friend who's a bona fide precision measurement physicist. His name is Peter Fuhlinger. He's from Munich. This is unpublished data that I have permission to show. Precision measurement physicist. For a living, he builds very good hypomagnetic chambers. Those are extremely good Faraday cages that can shield external magnetic fields in very precise ways. Again, magnetic field of the Earth is about 50 microtesla. Inside his chambers, the DC level is about 1 nanotesla. Okay, so he was starting to hear about magnetic fields in biology. So here's what he decided to do. He grew tadpoles for 2 days, and 2 days was the longest that he could go without asking for a bio permit because he's a physicist. He grew tadpoles for 2 days inside those chambers under 2 conditions. One, he imparted internally a magnetic field that was mimicking the magnetic field of the Earth. And after the 2 days inside this chamber, the tadpoles macroscopically looked okay. And in the second experiment, he grew a new batch of tadpoles for 2 days, just under this nanotesla magnetic field noise level. What he saw after 2 days was that and that's what you see there, in this case, about 1/3 of the tadpoles were macroscopically deformed. So let's think back about what this means. Here, we're not even imparting a magnetic field. We're taking out a tiny background magnetic field, the magnetic field of the Earth, with serious consequences as to how embryos develop. If the field is tiny, if there was something inside those embryos that responded like a tiny magnetite crystal to magnetic fields, because the magnetic field is so small, you would need to have had like a huge magnetic crystal that moves inside. Those huge crystals are nowhere to be seen in such embryos. They would be huge, like many microns across. Everyone's best guess is that this is somehow mediated by a spin phenomena then. And it turns out that melanin, the thing that gives the tadpoles their color, has very rich spin physics in it. There are other experiments done by the army showing that if you culture cells inside the hypomagnetic chamber, there are epigenetic markers such as DNA methylation rates that get changed in the absence of the Earth's magnetic field. So I hope you realize that this alone opens like a huge Pandora box of what this all means, right? From like how we can colonize other planets. If you want to grow tomatoes in Mars, reproducing Mars, what's the freaking magnetic field on Mars, right? To, like, is it possible to, and that's where we're going, and I'm almost finishing, can we deterministically learn how to tweak via weak magnetic fields those processes that might be depending on spin in physiology to actually get to a certain physiological result, right? To actually affect biology. So in 30 years, again, getting to the code book is hard. We need to get to the code book, to the atlas of what magnetic field is needed to tweak, what magnetic field strength, frequency, and direction is needed to tweak each chemical reaction. But in 30 years, I'm dead serious. I truly hope that we can grab our cell phones, open an app, and whoa, you need help with wound healing that has been shown to be spin dependent, to be magnetic field dependent in a way consistent with it being spin dependent. You click on your app, you tap your button. Oh, I need help with wound healing, and then you try it, Star Trek tricorder style like, and then you apply this to your skin or whatever. Again, this is the final product. Before we get there, we need this super high-tech quantum instrumentation thrown at those biological systems in order for us to understand unambiguously how and the extent to which spins are important for biological functioning. So this idea of shoving high quantum tech onto biology is being pursued by other people, some of whom I acknowledge there. I'm going to change by thanking my lab members and by ending this talk in the way that I always end, by saying, may the quantum be with you. What are your questions?
Amazing. Thank you very much, Clarice. This is so interesting. Just in the living world that we see, right? And we are not aware that there are quantum sensors in there that are crucial for all processes that are going on. And I was wondering, this must have happened somehow evolutionary, right? In birds. And probably it is amazing that birds can basically see the magnetic field. Now, some species are very close to them, for example, chickens, but they don't navigate as birds. Do they also have this cryptochrome gene?
But birds, I don't know. I would, if I had to take a guess, yes, because it appears everywhere. But you don't even need to go to birds, right? You talk about us. We have the hardware. I mean, if it's connected to a software stuff to sense magnetic fields, we don't know. But we have the hardware to sense magnetic fields. And again, what I want to make the point is that it's not only cryptochrome. Cryptochrome historically is the most well-studied protein. There's a whole other class of reactions and proteins that seem to be magnetic field dependent in a way that is consistent with it being driven by spins, right? So cryptochromes are good. They're super well studied. They initiated the conversation, but we need to start broadening this and thinking about this globally.
We are very curious for your vision there. We have talked yesterday with Celia Merzbacher from QEDC about the quantum ecosystem, computing, sensing, communication. How do you see, what is your broad view on the future of quantum biology and the quantum biology ecosystem?
The quantum biology ecosystem does not exist. I'm working hard to change that.
You are establishing it.
I'm establishing it. Well, not without a lot of pain and sweat, but that's fine. Pain, sweat, and blood. So here's the deal. Quantum biology is an aging field in that many people pivot to doing quantum bio experiments in their second half, in the last third of their career, when they're established, when they have a stream of funding more or less guaranteed. There are no standard calls for quantum biology. There is zero incentive for young blood to enter the field, right? And there's actually a disconnect, because what I'm advocating for is to throw quantum technology, quantum sensing like at least technology, onto those spins, degrees of freedom in biology, right? So it's actually, there's a disconnect, because experiments in biophysics, they are usually cheaper and they get done at faster timescales, right? Our experiments, the experiments that we're doing, they take 2 to 3 years to build, to get first results. They require as much money as an experiment in atomic and molecular physics. But the people, the regular quantum people, do not see us as belonging to their community yet, right? The biophysics community is what we're closer to, but they don't see us as fitting there either. So what I'm advocating for, this is really like, there are several flavors of quantum biology. Many of them are just electromagnetics in biology, right? So I'm advocating for us to start looking at those endogenous quantum degrees of freedom and treating them as quantum objects. Because before we get there, we're not going to be taken seriously by the quantum community, right? And that's what's needed. There is this big niche. I am super biased, but I'm super partial, but in my personal opinion, quantum biology is now where quantum computing was 30 years ago. There was a lot of theory, right? First experiments were first being started when Wineland did his first quantum gate with ions. He didn't sell, well, we're going to have a quantum computer tomorrow, right? So that is the long-term approach that I am advocating for quantum biology. What do we need to start doing now so that in 20 years, in 30 years, we get we reap the benefits for quantum biology research, for theranostics, for the advancement of quantum technologies based on strategies used by nature to mitigate noise, right? We need to start doing experiments, high-tech experiments now. We need to start thinking how to train interdisciplinary scientists, right? To maybe in 20, 30 years have quantum biology departments to be part of the broader quantum ecosystem as good members, as bona fide members.
Wonderful. And mind those words, where quantum computing was 30 years ago, it means it is a field in its infancy, which has so much promise ahead and a whole territory to explore. And everyone here heard the talk now and can include that in their own quantum journey to broaden it and explore also this field. There are more questions also about the basics, about connecting it to previous concepts, some clarifying, some broad questions. I will read some of them from Discord. In the middle of your presentation, you mentioned before thermalization kicks in. And before that, it was a good property. Johanna from Germany asks, is the sensor cooled down for initialization? How does it work before thermalization kicks in?
Yes, so the sensor is not physically cooled down. For initialization, it's not physically cooled down, but the effect is the same. I didn't have time to explain how the photophysics of the nitrogen vacancy sensor works, but by shining light continuously or for a certain time in the NV center, you end up doing spin polarization. What happens is that just by shining light, you make the sensor you make the population of the spin be concentrated in one level. That's how you do initialization, and that is sort of the equivalent of having it cooled down. And that's a good question. And I'm also going to make the bridge to the living sensor, because it's exactly the same thing for the cryptochrome photophysics. You always start in one particular state. So yes, you need some sort of initialization, and this is happening which is the same as cooling it down. And this thing happens both in the envy center and in the living sensor.
Yuchione asks, how quickly is it possible to change the phase of the driving field?
Well, that depends on, there's nothing fundamental about how quickly you can do this. It depends on your electronics, right? And it's not only how quickly you can change it, but how quickly, given the other timescales of your system, in particular, how quickly you change this phase with respect to the Rabi frequency, if you heard about that in your system. So it turns out that there are competing things going on with your envy center, right? And by changing how fast you turn the phase, you can actually give priority to certain, if you will, parts of your evolution of your Hamiltonian, right? So to cut a long story short, you can prioritize some interactions among with respect to others by changing how quickly you do this phase, and it's all understood mathematically, right? And this is why it makes that particular method so flexible, because if you can imagine that you have a sensor inserted into a sample, this sample can have different noise profiles. So by changing, if you understand the noise profile of each one of your samples, by understanding this noise profile, the experimentalist can change how fast it switches the phase to actually correct for different types of decohering noises.
Wonderful. Then about, is it one or more spins? Yusuf Germany asks, is the collective behavior of the spins understood in cryptochrome when exposed to magnetic fields?
No. In fact, the field is no. Short answer, no. It's actually not even known if it's one molecule that is cycled many, many times and senses the magnetic field, or if it's a lot of molecules that sense the magnetic field all at once. It's actually not known, like, if those molecules interact in some way, if they might have some collective interaction among them. That's not known. And that's the part of what attracts me to this field. There's so much to be discovered. And I think that by throwing quantum tech at those systems, there's so much that we can learn.
Amazing answer. I would have thought it would have all been cut out, but this is unknown, and everyone here can enter this field and do research on it. Here is a very interesting question from Nasser of Algeria, who says it was a great talk. Are there known correlations between changes in chemical properties in fossils from different time periods and the Earth's magnetic field flips? Could such a correlation be observable?
I have no idea. So here's another thing. So let me answer the question I wish you had asked, because I have been asked something else before. The magnetic field of the Earth is known to have changed, like, across many, many millions of years or something. People have asked me if bird migration patterns have changed as a consequence of this changing magnetic field of the Earth. I have no idea. I have looked for the answer to such a question. I have never found it. I am very curious about this, about fossils, about changes in bird migration. So if anyone finds the answer to this, please let me know. I'm very curious about that as well.
Great. Shoria Agrawal says, awesome session. Thank you so much. Masha Tosani says, many thanks. It was really insightful session for me. And Faiza from Turkey asks, what advice would you give to young researchers working on a better understanding of quantum biology?
I think the generic advice is keep curious, right? Keep curious, because now we are at a stage where we're getting to the very small scales, right? Enabled by nanotech. Quantum is popping up in so many different places that we hadn't thought was possible, right? So keep curious and keep trying to make connections. keep educating yourself not only in quantum but also in chemistry, in biology, right? And try to find connections that were not obvious to other people before.
Great advice. Prineha Narang said, keep your eyes open, and you say, keep these eyes indeed open, make the connections, be broad. Then if you get a few $1 billion now, what would your dream lab look like?
So I want to bring quantum biology experiments to the mainstream. I want to be the one to perform for the first time. That's what we're doing, but it's been hard at so many levels. Those quantum-inspired experiments onto biological systems. Again, I maintain that the field is going to remain bottlenecked while there's only correlative evidence for such spins phenomena in biology. The moment we throw quantum tech at those, treat those as quantum sensors that can be initialized, manipulated, and measured, this unlocks this huge potential for doing control, for controlling those degrees of freedom for so many things, right? And for people from the mainstream quantum side to start taking this field seriously, right?
On the chat, there are discussions if ants also use this to follow the path. It might be, right? And about different applications of quantum sensing. Fantastic. Thank you very much, Clarice, for this phenomenal talk and giving us insight in quantum biology. We'd love to have you back another time to discuss more with us and with all participants being present now and who will watch back your lecture later. We are very curious what the future for quantum biology will bring and your big contributions in it. Thank you very much.
Thank you all. And you can always reach me by email. My email is easy to remember. It's CLA, the first two letters of my name, CLA@ucla.edu. And I'm looking forward to seeing you again. Good luck with your quantum journey.
Thank you. Tomorrow we will talk more about that quantum journey because we have a career panel. Who is the quantum